Hello everyone, we are Team Lead 4 and we'll be talking about the dynamic Windows malware detection and prediction method based on contextual understanding of API call sequence. So what is a malware? A malware is a blanket term used to describe a malicious software and which is created by hackers with the intent to either disrupt, damage, or gain unauthorized access to computer systems. So hackers mainly design this to often compromise users' privacy or for financial gains. And we have several types of malwares. Every type of malware falls into a behavioral category. They are categorized according to how they behave. And the most common kinds include we have worms. Hackers basically install worm into a computer's memory to modify and also to delete data, and they can also be used to set up a backdoor for other cyber criminals to access the system. Then you have virus. A virus is usually installed as a Word document or an executable file and is dormant until an infected host, that's the user, activates it. Then you have the bots. The bots are infected computers. The servers, they can also be called zombie computers, and they are remotely controlled by hackers. Then the Trojan. The Trojan horse refers to a malicious file that disguises itself as legitimate. So you get a file and you think it's legitimate, but it's a Trojan horse. And a Trojan acts like a worm in the sense that it can wreak havoc on your computer or on your network. Then you have the ransomware, like the name describes ransom. The attackers limit access to your files stored on your computer and they demand a ransom for them to restore access back to you. Then you have the hardware. Most times people that download free software are most likely to come in contact with hardware, and the hardware basically slows down your device performance and it can also hamper your user experience. Then you have the spyware. The spyware is a form of a malicious software that gets your username, your password, and other data. And cyber criminals use this gotten or this stolen information to either carry out identity theft or credit card fraud. So the paper highlights a method to analyze, predict Windows malware using API call sequence by proposing a technique to reduce the number of API calls required to represent a sample. The paper addresses the challenge of constructing behavioral graphs for individual malware instances based on API call sequence. And to overcome this, the authors proposed a simplified behavioral graph generation by using word embedding for us to understand the contextual relationship among API functions. And they did this by introducing a method to cluster functions with similar contextual traits. That's functions that have the same traits.
The related work mentions that malware analysis methods include static analysis and dynamic analysis. The static analysis is checking the malware file through analyzing its executable binaries or codes without executing the malware. And in contrast, dynamic analysis involves executing the malware in a controlled environment, monitor the malware execution process, collecting, observing, and recording behavioral features. Dynamic analysis methods are typically conducted in a secure virtual environment known as a sandbox, such as Cuckoo Sandbox and Q Sandbox. The primary goals of these sandboxes are to examine the malicious behavior of malware while safeguarding the whole system from potential attacks. The static analysis and dynamic analysis each have their own weaknesses and strengths. The strength of the static analysis is that it's free from the overhead cost caused by program execution, and the weakness is the lack of support for packed and complex obfuscated code. The advantage of dynamic analysis lies in its ability to efficiently analyze packed and obfuscated malware as it unpacks itself during execution, loading its original and malicious code into the main memory. However, in commercial applications, dynamic analysis faces constraints when analyzing malware samples individually. This limitation may result in the consumption of time and resources. The paper focuses on dynamic analysis, particularly the examination of API call sequences during malware execution. It emphasizes the effectiveness of dynamic methods in capturing practical features for malware analysis, drawing a contrast between static and dynamic approaches for API call extraction. The study utilizes dynamic methods to collect API call sequences. The Windows API emphasizes that user applications in the Windows operating system rely on interfaces provided by dynamic link libraries, which means DLLs, like kernel32.dll and user32.dll, to access hardware and system resources, rather than accessing them directly. The Win32 API interface is identified in this figure, illustrating how a user program interacts with it to perform tasks. This paper provides an example. The Win32 API, depicted in Figure 1, is utilized when a user program needs to read a file. By invoking the ntread file function in ntdll.dll, the process triggers the associate service routine in kernel mode, also named ntread file. This implies that any program seeking a specific service will utilize the native API in kernel mode. The description of key DLL files is provided in this table. For example, kernel32.dll manages core functions like memory and file operations, while ntdll.dll serves as the interface to the Windows kernel, providing access to advanced functionalities for processes. The leading way to observe the program is to monitor API calls. The API functions by itself are standard. There are no categories called malicious or normal functions. The API call mechanism doesn't differentiate between malicious and normal programs. Therefore, this may pose a problem. How to determine whether the API call sequence is malicious or normal? The behavioral sequence of API calls can address this problem because this can lead to the contextual property of the calling process. However, this may pose a challenge. The number of functions, API functions is huge by itself. Therefore, it becomes tough to describe the behavioral attributes of running processes by tracking all APIs at the same time. The significance of API call sequences is as follows. The first, it can provide meaningful expressions that support and assist in better malware understanding. And the second is that API calls encode adequate information about the implicit malware functionalities which take place during the runtime of malware.
So essentially, what we're trying to achieve is um, working with API consequences, which are usually a lot of numbers, and trying to group them down to simpler factors so as to be able to work with them because it's always difficult to create a pattern when you're working with a lot of numbers. So the idea is to group them and then create sequence out of those groups. This can be best explained by describing a bag of rice, for example. It is easier for us to just cook rice and cook it than for us to give each rice different serial numbers, and each time you have to cook, you have to look for the exact serial numbers you want. So that would be quite ridiculous. So this model starts by the initialization phase, which includes word embedding. Essentially, these numbers, this bunch of numbers we're talking about, each is assigned words to represent them, and they will calculate the similarity between those words and cluster them together based on those similarities. So steps that seem similar to each other, we group them together, and the ones that seem out of line, we group them separately. So you wouldn't put rice and beans together. Moving on to learning phase. Learning phase is the interesting part. So now that we've been able to create a smaller group rather than all these lots of numbers, then it comes to how do we proceed from here. So each group is assigned a value based on what they contain. So for example, if it is about messages, you could assign it 5. If it's about attributes or files, you could assign it like a 2. So each uh, group is assigned a figure, and then we have this table, which is maximum likelihood estimation provided by Andrews et al. This is a previous research being referenced there. So essentially, if you've used log table, this will be easy for you to use. So we have two tables, one is for malware and the other is for goodware. So now, if you're moving from a sequence of 1 to 3, you can trace the probability of it being a malware. In this scenario, it is 0.0379, as you can see, whereas probability of it being a goodware is 0 by the time you trace it. What does this mean? Allow me to use this analogy to explain better for you. Imagine you're going to a Nike store and, typical steps, walk to the store, enter, go to the section you're looking to patronize, pick what you like, go to the cashier or self-checkouts, pay, and head out. So probability of the sequence following that pattern is quite high because that's the typical behavior. But when it comes to entering the store, see what you like, picking it, and rather than proceeding to paying, you decide to run out. Now that is out of character, and then that has a higher probability of being a malware because it is not following the recognized pattern. So that is the logic being driven by this learning phase. And depending on whichever is greater between the malware or the goodware, we assign a logical value to it. If malware is greater than goodware, we assign it a 1. And if it is the other way around, malware being lesser than goodware, we assign it a 0. The testing phase. This is quite important because now we've created a bunch of systems, but we want to be sure it's accurate. So now we have two Markov models, one representing malware and the other representing goodware. So each of these models have probability of zeros and 1. Remember, in the previous sections, we are going to convert this bunch of random numbers to zeros and 1. So these two Markov models hold the probability of it remaining in the same state or changing to the other state for both malware and goodware. And at the end, whichever we have the like addition of all probabilities, and whichever holds the higher value wins the race. That means if goodware, probability of it being a goodware is higher than malware, then we consider it as goodware. And if it is vice versa, consider it a malware. For an example, we'll look at Arial Mestosa setup, which is a common Windows file. So for this program now, this is the typical call sequence. And like I said earlier, nobody wants to look for the pattern between all these call sequences. So what we do is take it to the initialization phase, convert them into words, and then group them into like a broader topic for those words. So in this situation, we have pick message, we have message weights for multiple objects. So each of these groups contain objects similar to each other. So you can see, rather than having about 50 numbers, now we have 9 words. That is how dramatic this model is. And then this word, remember, we have assigned values based on their content. So these words have been assigned values, and these are the cluster sequences based on the value of these words. So you have pick message W, it has a 5 based on the content it has, message weight for multiple objects, 5, and so on. So now to the learning phase, the interesting parts. Remember this table I was showing you earlier? So now I have to zoom out because of the space, but there is the excerpt from it. So for this stage now, we check the probability of each value going on to the next, probability of transitioning, whether it is goodware or malware. Remember, based on the analogy I gave earlier, if somebody is leaving the store after picking something they like, most likely malware, or if they are going to pay, that seems more like a goodware. So that's essentially the ideology here. So for each item, 5 moving to 5, 5 moving to 5, most of it is repetitive. So you'd see here, in case you want to confirm, you can pause your video. But essentially, when we compare the probability of the malware and goodware, using this logic, we'll find out that in all scenarios, goodware outweighs the malware. Hence, the continuous zeros we have there. And for the learning phase, the testing phase, now we have these results, which looks good, but you want to double check to be sure. This is malware we're talking about. We don't want something to slip by us. Accuracy matters a lot. So we employ the two Markov models we spoke about earlier, which is malware model and the goodware model. And remember, we check the state of each transitioning and check the probability, add them together, and the one with the biggest value wins the race. So for this, it's straightforward 0 to 0, 0 to 0. So this is continuous 0.176 addition 10 times based on the 9 values we have here. And for this, it's 0.935. So no questions asked. It as expected. Uh, Goodware. It's recognized as a goodware because it has a higher value than the malware. And like I stated earlier, this is a known file and it's actually from Windows making prediction correct.
All right. Now let's go to the result and discussion part. So we can evaluate the module can correct, detect, and predict whether the given API consequence is malicious or not. To validate the approach, we can collect several API consequences. The experiments are carried out with different datasets of different size, with critical evaluation and metrics such as the accuracy, precision, recall, and add measure to evaluate the performance of the proposed module. There are also two additional evaluation metrics, including the false positive rate and the false negative rate to indicate the falsely predicted classes and the incorrect negatively classified classes. The experimental results show that the proposed work return a very high, accurate malware detection rate with very little false positive, as shown in the below table. This method returns an average precision accuracy of 0.99 with an average false positive rate of 0.01 and the false negative rate also 0.01. So this is very high proficiency in terms of detection the malware with great accuracy. Now, if we compare the proposed approach to previous works that rely on the API consequence, as shown in the below table, we can find that the proposed work outperform other works in terms of malware detection accuracy. Other works' results are ranging from 0.89 to 0.98, but this approach with very high accuracy of 0.999 considered the most accurate approach compared to other methods. Now let's check the malware prediction rates as well. So it's more effective if we can predict whether a given sequence is malicious or not based on its initial API calling function. Below table is showing the initial 50 API function that prediction feature in samples, and the model showed that the average accuracy of 0.997 with the average false positive rate is almost zero and the false negative rate of 0.007. This also proven that very high early prediction. So in conclusion, in this paper, the authors introduced to us a malware detection and prediction approach based on the contextual understanding of API consequence with three differences that Uthman described earlier, including the initialization, learning, and testing phase. So the results show very high accuracies in terms of both detecting and predicting malware. So in average, the detection rate average of 0.99 with very low false positive rate of 0.01. And it also shows the prediction accuracy of 0.997 with zero false positive rate and very low false negative rate of 0.07 as well. So in summary, this proposed work is considered as a very promising approach, not only to detect, but also to predict the malware based on this innovative methodology. So these are the references that the authors using for the works. You can take a look. And that's it for the presentation for Team Lead 4. Thank you, and it's time for Q&A in Canvas.